So this is going to be for page 16 of the C programming notes, but we need a handout from Learn. So I'm in the MTE 241 Spring 2020 offering. I'm going to go to Content, and I'm going to go to Lectures, and then to Lecture Handouts. Oops. So I'm going to download this so that I can mark it up. Alright, so this is going to be page 16 of the C programming notes, and so what we've got here is rules for developing safety critical code. So these are some guidelines that were developed by Gerald Holtzman at the Jet Propulsion Laboratory, part of NASA. They're famous for building things like the Mars rover and other stuff. So they build systems that have to be very reliable. They have had missions fail where they lost a rover, a satellite, and that's a very expensive thing to have happen. So Gerald developed a number of rules for developing code that's going to work, that's going to be reliable, especially in safety critical situations. And so these set of rules are things that they used at the JPL. So number one, use simple control flow constructs. So don't use go-to statements, those are bad. Don't use set jump or long jump constructs. So I'm not even going to teach you about set jump and long jump, but it's a way to do basically like try and catch that you might have seen in C++ or Java, to do that kind of control flow where it skips out of functions and it doesn't return level by level out of the function calls. It just jumps back to some predetermined location. And also direct or indirect recursion. Direct recursion would be function A calls function A. Indirect recursion is function A calls function B calls function A. That's indirect recursion. So why have these restrictions? Number one is code clarity. So you're writing code, and then other people need to go back and be able to read it, and you should be able to go back to your own work to make sense and to verify it. They often will do code reviews. I've experienced this myself on a project with Spar Aerospace. It's now called MDS Robotics. They did the Canada arm. We had a little project with them when I worked out east. And so we would do these code walkthroughs, and they'd say, why'd you do that? And you would explain, and they'd suggest other ways to do it, that kind of stuff. But another reason is for improved verification by tools. So they will use static analysis tools that will go through your code and look for problems with it, and so that makes that easier to do. Okay, with direct and indirect recursion, one of the drawbacks there is you don't know how deeply something can recurse. You might know, but you might have a logic error and it might recurse more than you expect. So when a satellite's off drifting through space, you don't want things that you tested a lot, but you don't want the possibility that something could happen that you weren't expecting. Okay, and for a similar reason, all loops have to have a fixed upper bound. So you can't have loops that you don't know won't have a maximum number of iterations, because they could impact the performance of other parts of the system if they run too long. So this will prevent runaway code. So you might have your normal test for the loop, like while I don't reach a certain value in what I'm processing, but then you would also have to add a maximum iteration count to the function. Okay, don't use dynamic memory allocation after initialization. This is common. So in the aerospace industry, in automotives, if you're going to get your application certified, you cannot use dynamic memory allocation. This leaves it a little open. Like, you can do it before you enter main, but not after that. I'm going to show you later in the course how you can statically initialize everything, so without using that. So the problem is that malloc can fail, so you can ask it to give you space and it can run out, or to give you some memory and it can just straight run out. Also, if you run the same function different times and you're calling malloc each time, it will depend on the state of the heap, the space that it has to allocate from, and that can change. And so you can get the same variable being allocated from different places, and it can cause different behavior. So the other advantage here is deterministic behavior. Okay, functions should fit on one page of paper, so this is for readability, clarity. Basically, when functions get bigger than that, it's hard for us to hold them in our head and to have a good understanding of what's going on. Okay, and the assertion density. So we haven't used asserts in this course, and I would guess that you have not used them in other courses, but an assert is a test of a logical condition, and if it fails, your program is terminated with an error message. If it passes, nothing happens. It's kind of like a null operation. It takes a little time to execute. So they are checks that you can add to your code to do things like test for reasonable parameters being passed into your function, other things like that. Assertions test for anomalous conditions. Now, if your code's flying through space on a satellite, you don't maybe want it to abort the program. That might not be a good thing, but it can log an error to memory, which can be checked from the ground possibly, or something like that. So this is an example here of the logical condition that is being tested. So this is our C code here. So if C assert p greater than or equals 0 is true, or sorry, not C assert. So if it fails, we're going to return error from this check here, and hopefully we'll handle that error in whatever called this function. And then down below here, this is the macro that defines our C assert. So C assert is actually a macro, and this test debugging here, this is a little confusing, but this would be something like printf or file printf, which just lets you printf to a specific file, or sprintf, which lets you printf into a string. So we're going to print, and we're going to print a string. So you see the %s there, and then we're going to print an integer. Let's just match up that %s with the file here. So this double underscore file, double underscore, there's 2 underscores on each end of that. That is defined by the C compiler for you. So that will be the file name. So this is the file name, and then %d matches up with double underscore line, which you can guess is the line in the source file where this test debugging is being used. And this is a macro, remember, so this C assert will actually be cut and paste into where we have the C assert up above there. So it will actually match the line of the if statement if it's going to log this error. So this is the line number in your source file, and these are defined by the C preprocessor, both of those. So that's kind of handy to know about. And so then it says assertion, single quotes %s failed. And what's the %s? %s lets us stringify E, and what is E? E here matches up with P greater than or equal to 0. So it's going to print out assertion, single quote, P greater than or equal to 0 failed. So when you see this pound E, this is going to stringify E. Okay, and so what this will print out is, let's just say it was in main and it was line 10. Then what it's going to print out is main.c, so it's the source file, 10, assertion, single quote, P greater than or equal to 0, failed. I'm starting to run out of room. So that's what you can expect this macro to print out if that assertion fails, and then we'll all return error. Macros are kind of confusing. They're kind of an ugly part of C, but in this case it's useful ugliness. Okay, number 6, data objects must be declared at the smallest possible level of scope. So this is the data hiding principle. So don't declare everything as globals. That would be kind of like the opposite of this rule. And again, this is for code clarity, and you don't accidentally modify variables. You don't have side effects where you're modifying a variable used by another function. That would be bad. Okay, number 7. Return value of non-void functions must be checked by each calling function, and the validity of the parameters must be checked inside each function. So again, this is to avoid or detect anomalous behavior. You're going to see in lecture that I don't always do this, just because the code examples will become too verbose and hard to follow. It does kind of obscure a little bit. This is where I think C really hurts, because it doesn't have exceptions. Exceptions, the try-catch behavior, are really good. In Java, you can't get away from them the way you can in C++. It's kind of in your face, and that's a good thing. It makes you deal with problems as they happen. Okay, the use of the preprocessor must be limited to the inclusion of header files and simple macro definitions, if you can call the above simple. So again, this is for code clarity, and I'm just going to say that it avoids something called obfuscation. So there are actually programming contests each year to see who can produce the most hard-to-read C program, and they're pretty impressive. I had a student in my CS 137 course once ask if he could obfuscate his first assignment, which was a really trivial assignment, and he used a whole bunch of preprocessor features, and you would have no idea what the program would do. So anyway, so don't make things hard to read. And simple pointers, there should only be one level of dereferencing, so you shouldn't have pointers to pointers or pointers to pointers to pointers, and no function pointers. So I talked about function pointers earlier, and we are going to see those in our real-time OS. We need that to pass a function to a thread that we're starting, and that would be probably the only exception to this. So just for an example, P arrow operator, dat arrow operator, x arrow operator first. That's, I guess, 3 levels of indirection, and so that would be verboten, not allowed. And the thing about function pointers is you can pass a function pointer to a function to execute, and then you can get different behavior each time depending what function you pass to it. So it can lead to less determinism. And finally, all code must be compiled from the day of the first development with all compiler warnings enabled. So let's underline that, all compiler warnings enabled. So usually the compiler warnings are just kind of like the common sense level, but you can have it check for everything. That's what pedantic does. It has to compile without any warnings. Sometimes you can think, okay, I'm getting this warning, but I understand it, it's okay. But that can come back to bite you later. So usually the warning's there for a reason. And all code must be checked daily with at least one, but preferably more than one state-of-the-art static code analyzer, which goes back up to point 1. Use simple control flows so that your static analyzer can understand your program and verify that it's logically doing what it should do. Okay, so that was the Power 10. Some good rules to live by, I guess. And that is the end of the C programming section of the notes.